Hi, okay, today we're going to be looking at our can combustor lab. The can combustor is, we're just looking at the ignition portion of a jet engine. Now the combustor itself is different sizes and shapes, which I'll cover in a minute. And what we have inside of our glass tube is a combustor out of a jet engine. We're going to be able to introduce fuel and measure the temperatures and the pressures inside the vessel using this lab. So I'm going to briefly describe some of the componentry and some of the apparatus that you'll be looking at in this lab. I'm going to quickly describe some of the apparatus that makes the laboratory run. This is our fuel tank. Our fuel tank is full of N-heptane. That's going to be the fuel that we're going to run today. And it's a pressurized tank. We have a nitrogen tank that is propellant to push the fuel through. We're also going to be using water in our calorimeter. And the water is in this tank, which is pressurized by compressed air. Okay, we're going to quickly look at our data acquisition system. Right here, we're going to be able to look at all of our thermocouples. We've got 10 thermocouples throughout the lab, and we're going to be able to move this selector and look at each corresponding temperature. Also, on our data acquisition, we're going to be able to save all the data. So the data that you guys are going to be converting is actually taken right here in this LabVIEW program. The fuel flow, you'll see, is right here. Now that's going to be the average. So on lab day, we'll actually take an exact measurement using this reader. Our airflow is also red right here. We have a 4.6 right now and a 4.6 right now. So all of our temperatures are red right here.
Let's take a look at the emissions from the combustor as we hold the fuel flow rate constant and decrease the airflow rate. Because the combustor is run in an overall lean state, decreasing the airflow velocity increases the equivalence ratio closer to stoichiometric. Additionally, decreasing the airflow rate and velocity increases the residence or the physical time of the gases in the combustor, allowing for more complete combustion. This figure shows the concentrations in parts per million of the unburned hydrocarbons and carbon monoxide in the exhaust as a function of time. About 200 seconds into the test, the airflow rate was decreased, and again at about 400 seconds. We see that the emissions of both unburned hydrocarbons and carbon monoxide decrease as the airflow rate is decreased. If we recall figure 9.2, we see that for lean conditions, changes in the equivalence ratio may not significantly change emissions of these products. The primary reason we see this reduction in emissions with decreased airflow rate is due to the increased residence time of the gases in the combustor. As seen in figure 9.1, if the residence time of the combustion gases is less than the time required for combustion, or the chemical time, the emissions of the combustor will increase. This figure shows the emissions of the nitrous oxide, or NOx compounds, and the carbon dioxide. The NOx emissions are reported in parts per million, whereas the carbon dioxide emissions are a percentage of the total exhaust gases. Here we see that both the NOx and the carbon dioxide emissions increase as the airflow velocity is decreased. This conforms to the idea that more complete combustion is occurring with a lower airflow rate. If we decrease the fuel flow rate and run the combustor for the same values of the airflow rate, we see that, in general, the same trends hold. However, the emissions of unburned hydrocarbons and carbon monoxide are much higher than for the previous fuel flow rate tested. The unburned hydrocarbon emissions increase from about 250 parts per million to about 1,000 parts per million, and the carbon monoxide emissions increase from about 250 parts per million to about 425 parts per million. When the fuel flow rate is reduced, the combustion is even leaner, resulting in low combustion temperatures and long chemical reaction times. Low temperatures will prevent the complete oxidation of the fuel, increasing emissions of unburned hydrocarbons and carbon monoxide. Longer chemical reaction times will also make it more likely that the residence time of the combustion gases is insufficient for complete combustion. So here we are seeing the effect of both time and temperature.